Buenas tardes. Perfecto. Micaela, no te preocupes. No veo el chat mientras estoy en la pizarra, así que si alguien no puede hablar, tendrá que esperar para que vuelva al chat de vuelta y vea las preguntas. A menos que alguno de ustedes sepa. Esperar un par de minutos más para comenzar. Si tienen alguna pregunta, sé que María Paula me mandó un correo que todavía no le he respondido, así que espero hacerlo ahora más tarde. Bueno, vamos a comenzar entonces. Okay, so yesterday we were looking at oh, my mouse is not responding here. One second. What's going on? Okay, so we were looking at anharmonic terms in phonon form. Okay, so remember that we had a term, the only way we can have phonon-phonon interactions, the only way to have phonon-phonon interactions is to have anharmonic terms in the Hamiltonian, because they will, they make available terms like this, for example. You have terms where you can create, okay, to create two phonons and make one phonon disappear like this, okay? So this would be something, a process which where I have a phonon initially Q3, and then we have two phonons dispersing symmetrically just because of conservation of momentum. Okay, so we can have a process like this. And if we have the other process where we have something like this and like this, so let's see, we would have two being destroyed. So let's suppose we have two being destroyed and one being created. Okay, so you could have a process like this. These two are being destroyed, and then we generate a a third. So we can have these two kinds of processes. So this would be the simplest possible phone-on interactions that we can have. Okay. And they would be, and we saw yesterday how this could arise from anharmonic terms in the expansion of the potential between the interaction between lattice sites joined by springs, by anharmonic springs. Okay, so I mentioned that we needed to have here conservation of momentum. So if we have a process like this, on the one hand, we need that Q3 is equal to Q1 plus Q2, okay? Or the same relationship here. And we also need conservation of energy, which is according to a certain dispersion relation that we have here, H omega 3 is going to have to be H omega Q1 plus H omega Q2. Okay, so conservation of energy and momentum, conservation of momentum. Okay, so so now the phonon-phonon interaction is available through these anharmonic terms. Nevertheless, let's see what happens to a current. So if we have a current of phonons, a current of phonons is a thermal current. Okay, so let's see if we can quantify a current of phonons, okay? And we can, this could be a vector quantity, okay? And a simple way to calculate the current of phonons is just to sum over the momenta of those phonons, okay? So we could have the momentum, okay, multiplied by the number of phonons which are in this state, in this particular state. Okay, so this is the number operator of phonons. Okay, and the eigenvalues. Okay, this would be the current operator, and the eigenvalues of this equation, that is the current that I'm going to measure, is going to be a function of, okay, the sum over all modes, then the vector, okay, just a simple, the classical vector, and then the number of particles that are here, number of particles. Okay, so if we evaluate, we can imagine sandwiching this between in the states Q, in a states Q, and this just evaluates the number of phonons in that state Q, multiplies them by the momentum, and we get the total current here. So this will be the measured current. Okay. Okay, so let's evaluate, for example, if we have a process like this. We have a Q1 plus Q2, okay, going into Q3, like we said before. So let's calculate, okay? So the current before the collision, let's state that one first, okay, before collision, okay, is going to be the sum, okay, Q1, okay, times one phonon, okay, one phonon there. So this is Q times one phonon plus, let me put here, more general. So Q1 times the number of phonons in Q1 plus Q2, okay, times the number of phonons in Q2 plus the sum over all the other states, okay, Q different from Q1 and Q2. Okay, Q and Q. Okay, so that will be the initial current before the collision. So this sums up, in particular, the phonons are in state Q1, in particular, plus the phonons are in state Q2, okay? And then we will have the sum over all the other phonons in the rest of the process. The thing is that this process only involves phonons in Q1, Q2, and Q3, okay? So, it doesn't matter what the rest of the phonons are doing. They won't be changing during this collision, okay? So after collision, what happens? This will be here. We call it prime, okay? So now we would have, okay, if after the collision, then we still have phonons of momentum Q1, but there's one less because one of those phonons disappeared in the collision process, okay? One of these disappeared. After the collision, one of these phonons disappeared, okay? So we would have that. Then we have Q2, also one of those phonons disappears, okay? And then we have we extract from this sum the Q3 phonons. So now, before we had Q3 phonons, okay? And now we have one additional one after the collision, okay? So this didn't exist before the collision, so we have an additional one there. And then we have the sum over, okay, all other phonon states. And here we separated also Q3, so Q's different from Q1, Q2, and Q3, okay, of the rest of the phonons that didn't involve themselves in the collision. Okay, so this would be now after collision, the current after the collision, okay? So notice that we can write this now. There's a question here, let's see, yeah, let's see, yeah. Okay, so what does Micaela say? Cuando haya silencio en la casa, le pregunto por el micrófono, si no, le escribo, okay. Okay, let's answer that at the end of the class, okay? Okay, good. So I can see when you're using the chat. Okay, so we have this balance equation. Okay, so let's see what happens with this guy here. Okay, so let's go to the next page. So notice, well, let's see first what's going to happen. So here we're going to have here this term here is the one we had before. This term here is the one we had before. Then this term here is the one we had before the collision also. So this would go into the summation, okay? And the rest, okay, so this times this one times this one times this one, plus this one is the previous current. We can even squeeze it in here. Let me put it another color. Okay, so this would be the previous current, okay? And then we have remaining minus Q1 minus Q2, okay? And then we have plus Q3, okay? But we know that from conservation of momentum, this guy is 0 because we invoke this relationship here. So this is 0, okay? So this the end result is that the final, the current after the collision is equal to the current at the beginning of the collision. Okay, so just by momentum conservation, we have that no matter how many collisions there are, the thermal current does not degrade. Thermal current does not degrade. Aha, we knew this result from from solid state 1, right? Remember that we needed anharmonic contributions in order to have a final thermal conductivity. Here we would have an infinite thermal conductivity. Okay, so we just initiate a current with an arbitrary small temperature gradient, and this current goes on forever. Okay, and we don't have thermal expansion also if we don't have anharmonic terms. But you see here that anharmonic terms by themselves are not enough, because if these anharmonic terms only involve conservative events, then they do not degrade the thermal current. Okay, so let's see what kind of processes, and I don't know if any of you remember what these processes are called. Okay, we can only have thermal degradation, the degradation of thermal currents. Okay, we can only have degradation of thermal currents if we have, okay, let me make an additional comment here. That is, the thermal conductivity is less than infinite if we have a Umklapp. And this guy must be a guy from the Netherlands to have such a strange name. Processes. Okay, what are the Umklapp processes? Remember that. When we have a phonons on a lattice, all the phonon degrees of freedom live within a Brillouin zone. Okay, phonons on a lattice, like electrons for that lattice. Electrons are waves and phonons are waves. Okay, so they live also within a Brillouin zone. Okay, so that's a lattice spacing. And here we have, for example, a two-dimensional case, not a one-dimensional case. Okay, although we can illustrate also Umklapp processes in a one-dimensional case, but let's do it a little more general. So this would be the Brillouin zone for the phonons. Okay, this is the Brillouin zone. Okay, so notice that here within this is the QX, for example, QY. Okay, so let's suppose we have a process like this. So this would be, we draw it with another color here. So if we have some process here with Q1, okay, and then some other process here with a Q2, that's easy to draw. So the parallelogram gives us Q3, it's going to be here. Okay, Q2, and this would be Q3. Okay, so these processes here do not degrade the thermal current. Okay, but if we have large enough vectors, for example, let's suppose we have Q1 here and Q2 is very large in comparison. Okay, it's almost at the edge of the Brillouin zone. So when we add the two, we have a vector which is outside the Brillouin zone. So you know that so this would be outside Brillouin zone. Okay, so any conservation of momentum within the lattice is not like in free space. The conservation is up to a vector of the reciprocal lattice. Okay, so we could have then a process which instead of obeying the regular momentum conservation rule on a lattice, this is conserved to within a reciprocal lattice vector. Okay, remember this from solid state 1. So this is the difference between conservation laws in free space and conservation laws in a discrete space. Okay, so in discrete space, you would have a discrete periodic space, you would have a reciprocal lattice vector, and the smallest the reciprocal lattice vector is a condition that can enter into the conservation of momentum. So this would be the Umklapp process. Okay. And then what happens? Then in the previous relationship here, this difference here is not necessarily 0. Okay. And then we have that are the phonon current, okay, prime, can be the previous phonon current plus a reciprocal lattice vector. Okay, how do you see that this is actually degrading? Because when we, this point out here should be equivalent to a lattice vector inside, okay? So when we draw this vector back using the reciprocal lattice vector, it will turn out to be opposing. It will be something, let me put another color like this. So this will be the equivalent position. So see this one here. Okay, so it will be something like this. Okay, so no, we can, yeah, let's draw one that makes more sense here. So we can return this one. So this will be, this extension here would be a reciprocal lattice vector. So we can return this one going on here. So you see that there's a component of the reciprocal of the vector inside the Brillouin zone, which opposes some component of the initial momentum. So it's non-trivial how this current is being degraded, but then you see that this vector here is equivalent to this vector here. So you see it's not in the direction of the original momentum that are being summed up. Okay, so this will be my new associated. This will be the new associated with the new phonon current. Okay, so this is the way you manage to change. So this changes the initial current, initial thermal current. Okay. Okay, so this is just a comment. This is the same result you saw in solid state 1, but always stated in second quantized form through the processes that generate these phonon collisions, and then how the definition of the thermal current or the phonon current, which we just found out how to do also in second quantized form, and the implications of that definition of thermal current and how that gives rise to the need of having Umklapp processes in order to degrade the current. So this is just the same phenomenon you saw in solid state 1, but now written in terms of second quantization. Okay? Do you have any questions? Those who can speak? Okay, no questions? Okay. So let's go now to the Holstein model. Holstein. Okay, so We will learn here how to now devise models in second quantized form. Okay, so we will have a couple of comments on the model and some other phenomena associated with now electron-phonon interactions. Okay, so this is actually going to be about what are called in physics polarons. Okay, and polarons are a limit of the electron-phonon interaction. Okay, limit when it is stronger than kinetic energy of electrons. Okay, we'll write that out explicitly. Okay, and the interesting thing about this process is that it's a very generic process of how charge gets transported in molecules, for example. So this would be an example, okay, or let's put it, it's relevant for charge transport. In general, I would say in low-dimensional systems. Okay, so although it may look like a toy model, okay, it's a toy model like, you know, like the Einstein phonons, which are actually very good approximation to optical phonons. Okay, okay, so what is going to be our model? Again, we're going to start with the Einstein model. Einstein phonons. So this is Einstein phonons have resulted as everything that, you know, Einstein did. Even when he was wrong, he made something, an interesting statement. Okay, so we start with Einstein phonons. Okay, and in Einstein phonons, as we know, you have independent oscillators. Okay, so let's draw these oscillators like this. Okay, maybe a little more detail that is needed for an Einstein phonon. And this goes on, okay, in both directions like this. So this is a one-dimensional system. Okay, and we're going to label them. So we're going to assign site I here, site I plus 1. Okay, site I plus 2. So the labels we're going to use are site labels. Okay, and of course, if this is displacement here, so we have a U2 displacement here, and we have a U1 displacement here, associated with the side with the. Sorry, I put I plus 2, should be I plus 1 here. Okay. Then we're going to have a label associated with that particular site, which is going to be the displacement is going to be U2 minus U1. Okay, so we're going to use this variable x to express the difference between the two displacements. Okay, and we'll use that as a variable for our chain Hamiltonian. Let's call this chain or HC. Okay, and that chain Hamiltonian is going to be just a regular harmonic oscillator. Okay, so we have the sum of the momenta associated, the total kinetic energy associated with the motion of both particles at the site, okay, with a mass m, okay, and then we're going to have the potential energy, m omega 0, and then we're going to have the label like this, okay? So these are all oscillations inside. Again, this would describe the oscillations of an optical phonon. Okay, remember the optical phonons are determining the physics of the internal the base oscillations. Okay, somebody was asking something here. Okay, when I want, when I don't want, I manage to invoke this. And here it goes. Okay. Does exist another model where we do not consider the motion as harmonic oscillator? The thing is that the harmonic oscillator will be always there, right? So we could have, for example, remember here that we're going to introduce I'll tell you why we're introducing harmonic oscillators here. So we'll have electrons on one side, we'll have phonons, okay? So electrons alone, we know how to describe, okay? Phonons alone, we know how to describe, okay? Then we take into account deviations from the harmonic oscillator by considering the interaction between phonons and electrons. So that will be already a deviation from the harmonic oscillator because we have an additional coupling, okay? And remember that in the previous section, we already considered terms like this, okay? So that's no longer a harmonic oscillator. These are harmonic, unharmonic corrections, okay? So we already considered what would happen when we have this. We will have phonon-phonon collisions, and we have other types of processes. Okay, but for now, we're going to consider a reservoir of phonons, a reservoir of electrons, and we're going to have that these phonons are going to be Einstein phonons. Of course, we can consider complications. We can add these kind of terms in the Hamiltonian and deal with those terms also. We'll see a particular limit of this in a second, so you can see that we can take, for example, assume that this mass is very large, so we discard this term here. So we don't really have a harmonic oscillator, but we have some potential energy, some over-damped, for example, a spring that is only described by this term. So we'll see a little more about that in a second, okay? But of course, we can go beyond the harmonic oscillator problem by considering these types of corrections to the harmonic oscillator. Okay, so we know how to proceed in this problem in second quantization, okay? In second quantization, what would we do? Well, what we do is that the harmonic oscillator part of this problem we address like this. Okay, so we make up this ladder operator, which is related to the classical variables, to the canonical variables x and p, as in the following way. Okay, so this would be xi. So this is associated with creating, okay, a vibration in site I, and this is the coordinate of site I, and then we have the momentum of site I. Okay, so we saw this already in the case of a particle in an external electric field, a spring in an external electric field, and then we have the corresponding relationship for the creation operators, which have the same coefficient here, but then we have just a change in sign here. Okay, we take into account that these, from the commutation relations of the canonical variables x and p, okay, we get that the commutation relations for these operators, now we have commutation relations, okay, will be delta ij, okay, and the rest of the commutations are 0. Okay. Okay, so we have this, and we know, and I'm going to, although we haven't done explicitly, we did part of the exercise in class. Okay, you know that then in second quantization, the chain Hamiltonian will be described by H omega, okay, AI dagger AI plus 1. Okay, that will be the second quantized form of a harmonic oscillator. And that's obeyed by just the Einstein phonons, okay? So vibrations of this lattice, we sum over all the lattice sites, whatever the occupation number of each oscillator is, and we multiply by H omega 0, and we get the energy of the system, okay? So now let's add electrons, okay? We add electrons. Okay, and here's how, I mean, we don't focus here on going beyond the harmonic oscillator because we are interested in the electron-phonon interaction. So let's see what's happening there. Okay, so so we add electrons. So let's suppose we keep these electrons and the phonons away from each other. Okay, so we have here the Einstein oscillator and the electron, okay, far away. Okay, from each other. Okay, so they will have an energy associated, okay, with whatever the energy associated with the vibration of this and the kinetic energy of the electron, which doesn't interact with anything else. So far away, we call this energy, okay? So this is the energy for electrons and phonons, okay? Energy, okay? This is the energy for that. Okay, now we put them together. Okay, and so we have the Einstein oscillator, okay, and we now put in the electron. We put the electron close to that Einstein oscillator, okay. We have that the oscillator, okay, is neutral, so this is neutral, okay, but it can suffer a redistribution of charge due to the fact that the electron is getting closer. So we're going to assume, okay, that when the electron gets closer, then we get a deformation of this spring, okay? So this suffers, okay, suffers a deformation X. Suffers a deformation X, okay? So let's see how we model this. And we're going to assume that when the electron, okay, so we're not going to go into too much detail of how, what the microscopics of these interactions are, but that when the electron gets close to the spring deforms and the electron is attracted to that deformation, okay? This we saw already in, I've described the mechanism for superconductivity. For example, you can assume here that we have a uniform charge here and we have two ions, okay? So the ions are fixed. When I bring the electron close, it pushes away the negative charge, exposes the positive charge, and those opposite charges attract. So we are going to assume that this is an attractive interaction, okay? How are we going to model it? We're just going to do a little dimensional analysis, okay? Dimensional analysis. Okay, remember we always left indicated the electron-phonon interaction. We assumed that it was, for example, it could be a Coulomb interaction, but we always left indicated what that interaction was going to be. Okay, let's see. No, we said neutral position, no, neutral charge. In this previous one, neutral charge. Let's call it the other way around. Ah. What did I do? Oh, I just switched pages. Okay. I was scared there for a second. Okay, so let's put that the spring is charge neutral. Let's put it down. Charge neutral spring. Okay, just like in a solid. Okay, we have as many electrons going around as ions in the fixed sites, so that would be as a whole charge neutral. And then we add an electron there, and we see what happens to the system. Okay. So let's do some dimensional analysis here. Okay. So we're going to model the changes of energy due to the interaction between the electron and the phonon. So this is going to be the first approximation, okay? The energy with the electron and the phonon very far apart. If the spring is charge neutral, how the interaction will be attracted, okay? So that was what I tried to explain before. So let's do it in a little more detail. Okay, so imagine I imagine that we have the spring like this. Okay, and we have, if it's charge neutral, this means that we have as many negative charges as we have positive charges here. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so charge neutral means that we have as many negative charges as positive charges, right? So imagine, as we regularly do for a crystal, that the positive charges are fixed and the negative charges are mobile, right? So if we now add an additional electron, okay, then we can have something like this. So the positive charges stay where they are, while the negative charges are going to accumulate here, okay? So because this negative charge pushes the other ones away, and it gets attracted to these guys. So this is how we generate an attractive interaction. Okay, so these charges get pulled away, and we have this negative being attracted by the positive charges, and we get a bound state. Okay, you see, this is not a very strange situation, because, for example, atoms are charge neutral, okay, when they're not ionized, and nevertheless, all the electrons are bound. So this is a lower energy state. Okay, so this is how this could happen. Okay, but again, we're not worrying too much about the detailed model. We're just saying, okay, somehow when the electron gets closer, and these negative charges, for example, push these atoms away, and you generate an X deformation. Okay, so you stretch the spring, and you get an attraction. Okay, so I'm going to put here an attraction, so this lowers the energy. Okay, and I'm going to put this as a combination of the known quantities in my system, which I will write like this. And we will just check that we have the correct dimensions. Okay, so we have, like in a Taylor expansion, right? In a Taylor expansion, we would have Ex is equal to E0 plus the derivative, okay, of the energy with respect to this distance evaluated at x equal to 0 times x, okay? So I'm just telling you that this derivative here, I am modeling this way, okay? Notice I use the mass of the harmonic oscillator, the frequency, the natural frequency of the harmonic oscillator, the Planck constant, and then I make up this coupling here, which is telling me how strongly these guys are going to couple, okay? So let's check out first that these dimensions are correct, okay? So from this previous relation. Well, let me just do the dimensional analysis directly. So what are the dimensions of this guy? This guy here. So we have 2m, 2 does not have dimensions. We have mass, we have frequency, and we have Planck's constant, and we're going to analyze the dimensions of this quantity here. So we're leaving the dimensions of G outside. We don't know those dimensions yet, okay? And we want now the dimensions of the quantities inside here. So we have the dimensions of mass, okay? Dimensions of frequency, okay? And dimensions of Planck's constant, okay? And we're going to include here, we forgot the x, so the x is outside the square root, and this has dimensions of length, okay, dimensions of x. So we leave this alone, okay? This is just mass, dimensions of mass. This is dimensions of 1 over time. And this has dimensions of length, okay? Length, let me put the square of length times momentum, which is mass, okay, times velocity, okay? And this will be multiplied outside by dimensions of length, okay? So what are the dimensions here? So we have dimensions of G, we have m squared, L squared over T squared, so this will be dimensions of m times L over T, okay? And this times L gives me again mass times velocity times length, so this has dimensions of angular momentum, okay? So what should be the dimensions of G? If we're going to get an energy out of this, this should be an energy, right? So this should have dimensions of 1 over T, over frequency, okay? So this would be H, has the dimensions of H omega, okay? And that will be an energy, okay? So if we choose G to have dimensions of 1 over time, we would have dimensions of energy here with the selection of parameters that I chose here for the square root, okay? Is that clear? Okay, so this is an exercise you should be able to do since, you know, at least by the end of the Common Core, you should be able to do this kind of dimensional analysis, which is very useful for many, many physical problems, okay? So we choose our parameter here. We know that G has dimensions of frequency, and the rest of this, including the X, has dimensions of angular momentum. So angular momentum times frequency gives me an energy. Okay, so now we clarified that up, okay? So notice the ingredients we have. So now we have a deformation, so this will be described by phonons, okay? This will be harmonic oscillator excitations, okay? And this is a coupling to an electron, okay? So this just is going to count the number of electrons that are in the oscillator times the deformation of the oscillator. And that's the electron-phonon interaction. So let's write that out. So this was a kind of a more intuitive derivation of electron-phonon interaction. Okay, and you see that again with the question that Michaela made, we could also always add here further higher order terms in the expansion, and we can include corrections to the corrections and or higher order interactions, or because of some particular case, we have that the lowest order doesn't exist. We have the quadratic orders, or we would have another type of model in that case, okay? So that we can correct also systematically. Okay, so now our interacting Hamiltonian is going to be minus, I always put the minus here because it's an attractive interaction, times square root of 2m, okay, omega 0 h okay? And then we have sum over all the sites. We have the occupation by electrons of the sites, okay? We know that they can be 0 and 1 for the case of fermions, okay? And then times the deformation of that particular site, okay? So that will be my Hamiltonian in second quantized form. Just 1 second here, I need to close the window. So this is a slightly less sophisticated version of our electron-phonon interaction, because the previous case we had this, the fermion operator was not necessarily diagonal, okay? But this has essentially the same form, couples electron degrees of freedom with phonon degrees of freedom, okay? So this is a fermion boson coupling, okay? In order to finalize the second quantized form, we know that this we will have to put in terms of phonon operators or boson operators. So this is going to be a symmetric combination of creation and annihilation operators of bosons, okay? So finally, we can write this one. And as there's a coefficient here, okay, related to the inversion of this relationship here, okay? So we invert this, we, for example, add these two equations, so we cancel the momentum, and we get now x in terms of A and A dagger, so which is going to be uniform. So this the prefactor is just going to be this 2h over m omega, okay? That's very easy. So just substitute x here, and you get something that I will be calling G twiddle, okay? Sum over I, Ci dagger Ci, and then we have AI SAI dagger. Okay, so this is the electron-phonon interaction that we're going to analyze. Okay, so we add the remaining ingredients. So we have to add add now. Okay, so we have the phonon, the harmonic Hamiltonian as a pure phonon contribution. Then we have the electron-phonon interaction, which is this interaction here, and we add now electrons on a lattice. Okay, and so this will be the full Hamiltonian that we have to solve is going to be this one. So I'll first write the only term that I hadn't added before. So this will be the electrons on a lattice plus the conjugate. Okay, this will be the electron Hamiltonian. Okay, so the electrons can hop from one side to another. Put here like this. Okay, so this means that they just hop. So this is pure kinetic energy. Okay, kinetic energy. And the only interaction with the lattice is through the electron-phonon interaction. Okay, so now we add the electron-phonon interaction with G twiddle sum Ci dagger AI plus AI dagger, okay, plus the harmonic oscillator term. Okay, and then after writing this, we're in business, okay? If we are mostly interested in studying the electron-phonon interaction, it's enough to put the harmonic oscillators and approximation, and then the purely kinetic energy of the electrons in this case. Okay? Any questions here? Okay, so this is the Hamiltonian we want to address. Okay, so this is a very difficult problem, okay, very difficult problem. In general. And we will solve it, so we will solve it in a particular limit. Okay, that limit can be expressed essentially by saying that G twiddle is going to be much larger than the kinetic energy of the electron. So the electrons tend to be trapped, and that's a Polaron limit precisely, okay? So we could have, for example, if the kinetic energy was very large, then the electrons would move along this model. The electrons would move along this lattice very easily, okay? And only be perturbed by the electron-phonon interaction. The Polaron limit, okay? Polaron limit, okay? Electrons tend to stay stuck on lattice sites, okay? And the T is, the kinetic energy is a perturbation. So from time to time, and this is how molecules actually conduct, from time to time, so let's draw here the model that we have. So, okay, so from time to time, the electron gets trapped here, and then from time to time, it jumps between two sites, and then it becomes another polaron in the other site, and so on, okay? Those who have processes like this, okay? So T is telling me how the electron jumps from site. Remember that we labeled the sites like this, okay? And so the T is telling me how the electron can jump from one side to another, and then the other terms are telling me how the electron interacts with the individual units, okay? So this is the Polaron model. And so here we have a coupling G tilde, and G tilde is much larger than T, okay? So we're going to treat the electron kinetic energy as a perturbation here. Okay, there's one limit which has a lot of physics also, which, I'm going to call this the Piles model, okay, which is one limit, okay, limit of Holstein model. Okay, and I just mentioned this because you'll hear it a lot if you go to graduate school about the Piles instability, okay, which can be a nice, also a nice project for the final report, okay. And in this model, we're going to in this limit we neglect the harmonic oscillator kinetic energy. Okay, so it's purely potential energy, purely potential energy. Okay, so this is a limit also, which is particularly simple because we can write if this, let's call this a Piles Hamiltonian, the Piles Hamiltonian. We would have the electron Hamiltonian as we had before. Okay, so we have Ci is 1 plus. Okay, so we have the kinetic energy, but then we're going to have then the electron-phonon interaction, the same as before. Okay, but then we take only from the harmonic oscillator, we take only the potential terms. So this will be K, we call this K twiddle, and you know that it's going to be some K times the deformation only, so this will be the deformation squared, okay? So this is only potential term. Okay, so what happens here? If we only have this term here, then this is x. Remember, this is the proportional to x, and this is proportional to x squared. Okay, so you see that this Hamiltonian, then the x is going to be a good quantum number now. The position is going to be a good quantum number, and in principle, okay, this means that the eigenfunctions after the Hamiltonian are going to be eigenfunctions of the position, okay, because the position operator commutes with the full Hamiltonian, okay. Remember that the phonon degrees of freedom are going to commute with any fermion operators, okay, and then they're going to commute with both of these terms because those terms are proportional to x, okay. So this means that H full, and this is an analysis you always need to do before you start the problem. Okay, remember that we've always treated interaction. We did many examples where the interaction commuted with the H0 Hamiltonian, so they had common eigenstates, and we could solve those Hamiltonians very easily. Here is the same thing. So the full Hamiltonian commutes with x. Okay, let me not put full Hamiltonian, let me put Piles Hamiltonian. Okay, commutes with x. Okay, this implies that eigenstates of H are position eigenstates. Okay, so this is in the same spirit as the perturbations we illustrated, the very simple perturbations we illustrated in previous classes. Okay, so in this case, nevertheless, this turns out to be a very surprisingly difficult problem. Okay, why? Because you would assume, okay, intuitively, this problem we're not going to solve it intuitively. Then we would have a solution like this. A solution that goes like this. So we have the oscillators, okay? Okay, and if we sprinkle electrons along this system, okay, then we expect to have as many electrons distributed uniformly here, here, and here, okay? So intuitively, this is what we would obtain, okay? And we have, so that we have electrons in well-defined positions at each space, at each point in space. Why would we distinguish one point in space from another? Okay, there's no way to distinguish one point in space to another. So we would have a uniform charge distribution. Okay, so this is the physical analysis. The problem is that for one-dimensional systems, okay, but 1D systems. And this is a problem of quantum fluctuations, which you will also learn about in more advanced courses, okay, in your graduate school. You have that the so-called Piles instability. Okay, so that you see that quantum almost never conforms to the intuition that you have to calculate. So many times the professors, you know, the students start asking questions, and the professor, that's a joke, of course, tells, shut up and calculate. Okay, so this is many times the approach in quantum mechanics. Okay, it's very difficult. So the actual solution is something like this, that all the charge density, there's a large charge density here in one of the oscillators, and then there's a small one. So charge tends to localize. Okay, due to the piles instability. There are various forms of this piles concept, the instability, and the important thing is that it's most important in 1D systems, okay? Higher dimensional systems do not exhibit this kind of instability, but for 1D systems especially, you get this type of solution. So there's non-trivial, okay? Non-trivial solutions, although the Hamiltonian seems very trivial, okay? So this I just wanted to illustrate to you that even in some simple limits, so sometimes we think, okay, we'll oversimplify the problem, we won't obtain anything, you know, extraordinary. But in this case, we do. I mean, here we obtain something that commutes with the position eigenstate, okay, commutes with the position operator. So it would seem that we would obtain very simple solutions to the dynamical equations. Nevertheless, you see this kind of a very strange phenomena going on, and that's just because the quantum mechanics is not free ever from fluctuations. Okay. Okay. So let's start with the just stating the problem we're going to solve. So we're going to solve the heavy Polaron limit. Okay, as I said before, okay, so we have the Holstein Hamiltonian, okay? The Holstein Hamiltonian will have its harmonic contribution. Okay, so we have AI plus 1/2. There's a harmonic oscillator. Then we're going to put the electron-phonon interaction, okay? It is going to be proportional to the electron occupation, and then the deformation of the spring, okay? And then finally, we're going to have the kinetic energy of the electrons, okay? Ci plus 1, then Ci plus Ci dagger. It is the other way around, but it's the same thing, right? We're adding the two objects. Okay, and we're going to take the limit in which t is much smaller than g. So this is going to be a perturbation. Okay, and then we're going to try to diagonalize these two operators together. So this is going to be the feat that we're trying to achieve first. Okay, so we diagonalize this. We find an eigenbasis for this solution, for this diagonalization, and we substitute that solution into the kinetic energy operator, and we just find the form it has. Okay, so this is going to be the problem we're going to solve, and we're going to do this through a canonical transformation. Okay, this is going to be a more generic form of a canonical transformation. Of course, this change we did between one set of operators and another set of operators that conserve the commutations or anti-commutation relations, where one form a sort of a linear canonical transformation. Here we're going to do a unitary canonical transformation in order to obtain the solution to the problem. Okay? So the statement of the problem is going to be really easy, okay? And then we have to do a lot of algebra in order to obtain the solution, but straightforward algebra, okay? So we concoct a transformation following form. Okay? So this is a very generic form of a canonical transformation. We essentially sandwich, okay, the old operators, which are going to be the regular fermion operators, okay, between two exponentials of an operator, okay, where S is to be found, okay, and we generate, so these are the old operators, okay, of the non-diagonal Hamiltonian. Notice here that we obviously have a non-diagonal Hamiltonian here, okay. This will be diagonal only in phonon space, but then in the combined fermion boson space, this is a non-diagonal form, okay. So we want to diagonalize. So in principle, we set up this S function here of operators in order to obtain new operators in which the Hamiltonian is diagonal. Okay, and we make up new operators also B, which we will call B, which is a sandwich between the same operation, okay, of the old boson operators, which will be of this form. Okay, and this is the new operators here. Okay. Okay, so this depends now on a very special form of this S. Okay, and we have to make up. There are some transformations, some canonical transformations that allow me to diagonalize order by order, which is what I mentioned before with the Foldy-Watusen or the Schiffer-Wolff transformation. Okay, here we rely on the creativity of Holstein, so creativity of Holstein, who, after doing lots of, sitting down in a chair, he found out this operator here, what the appropriate form of that operator was. So this, the form of the operator is going to be this one. And we're just going to show that using this form of S, I can diagonalize the system. So this is many times what you do. So you'll get famous if you make up one of these transformations yourself to solve an interesting problem, okay? So this is one of the emblematic transformations in condensed matter physics, okay? This is going to be the number operator, okay, the fermion number operator, okay? Okay, remember this is going to be just Ci, and has a label I, Ci. Okay, the number operator. And this is going to be this particular combination, which looks like momentum, looks like a momentum operator. Okay, just by looking at the transformations here, remember that then we could multiply the second one by a minus sign, and then we add the 2 and we eliminate the x variable here, and we only get momentum. So that's why I call it momentum-like. Momentum-like. Okay. Any questions up till now? Okay, so I'm just telling you the recipe here. we're going to, this is a very generic form, but the particular choice of S can be very different depending on the problem, okay? And this is given either by God or by Holstein, okay? Somebody tells us that, or we work it out just by, you know, looking at the problem for a long time, working out things for the long time. Okay, so let's see what kind of operators these are going to be. So we know that these are fermionic operators, the C, and these are bosonic operators. So let's see what the nature of P and B are, okay? And this is one thing that's going to be preserved under this canonical transformation. So let's see what the commutation relation of the P's are, anti-commutation relation. Okay, so what is this? Okay, this is the first of many exercises like this we're going to do in the context of these problems. And in the process, we're going to learn lots about how to manipulate in second quantized form. Okay, so we just substitute the meaning of the P. So the meaning of the P is IS. Okay, and this is going to be Ci e to the minus IS. Okay, commuting with, okay, with e to the IS again. Okay, and then we have Cj dagger e to the IS. Okay, so let's see what this means. Okay, so we just spell it out explicitly. So it's e to the IS, Ci e to the minus IS. Okay, times the other guy, so IS, Cj dagger, e to the, got a minus sign here, minus IS, okay? Okay, this will be the first ordering, and then we have minus, plus, because it's the anti-commutator, and then we have e to the IS, Cj dagger, e to the minus IS, and then multiplied by the other one is e to the IS, Ci e to the minus IS. Okay, that would be like this. So we know that then these two operators give me just the unit operator, okay? And the same thing happens here, okay? So this will be e to the IS, Ci, Cj, dagger, plus, times e to the minus IS, okay? Plus, then e to the IS, Cj dagger, Ci e to the minus IS, okay? And then this can be written like this. We just have the sandwich of both operators like this, plus okay. And we know this because we know the original, the original commutation relations, anti-commutation relations. This is going to be just the anti-commutation relation of this. And this is delta ij, okay? So this whole thing is equal to delta ij. Okay, so this means that the original operators are fermions, and the new operators are also fermions. Okay, so this is a condition again, but that it's already built in to this this transformation. It's built in that we preserve either the fermionic character in the case of P and the bosonic character in terms of A. Okay. What other things do we have to notice immediately in order to proceed and simplify things? What is let's go back to S. Okay, so S we found out like this. Let's see what S dagger is. Okay, so S dagger is very simple. We just dagger these guys. Okay, so this becomes A minus AI dagger. Okay, So this changes sign. This number operator dagger is the same operator, okay? G dagger, G is a real number, okay? And we get an I here, okay? And we get the same combinations here, okay? But now we invert this guy again. And so we take out a minus sign. And so we put it in the front. So we get the same operator. So this will be S. So S is equal to S dagger, okay? This is another built-in property that here of the form of this operator here. So now we can use this wherever we need it, okay? What other relationship is interesting? Another relationship that is interesting is that we dagger this guy, okay? This means that we have this relationship here, okay? And we dagger it, okay? Let's see how we proceed. Remember how we did this? So this would be just the permuting. So we put these two together, for example. So we do it by pieces. So this would be IS dagger, okay? And then e to the minus IS dagger, but we know IS dagger is the same as IS, okay? So let me just do it step by step. So now we have to dagger this guy. So this would be minus IS dagger, okay? CI dagger e to the minus IS, because IS S dagger is equal to S, okay? And then we dagger this guy, and we dagger this guy, which gives us IS dagger, CI e to the minus IS, and then finally this is equal to IS CI e to the minus I. So you see another property of this transformation, which is interesting, is that if you dagger the new operators, you just dagger inside the transformation, and the rest of the transformation is left without any change, okay? This is also true for the other guy. The other guy, if you dagger this guy, and you can just prove it using the same logic, okay? It's just daggering the inside of this transformation. Okay, is this clear? Okay, so I leave you to prove, and of course this will be in the problem set number 4, that the commutation relation, okay, now for the bosonic transformation, indeed obeys the same commutation relation that the original bosons obey, the same commutation relations that the old operators for bosons obey, okay? Any questions up to here? Okay, so this should be very, very good practice. At the end of this section, you're going to be real masters of the commutation relations. Okay? Okay, so I'll just introduce an additional variable here, a more generic way to treat all the possible commutation relations in the problem by just stating a generalized function, okay? So let me introduce this function and we'll prove a bunch of properties next class. Okay, so let's introduce now a generalization of that transformation. We'll call it F, and this will be F of some particular operator, okay? And I'm just going to generate in a very trivial way. We're just going to put a parameter alpha here, which is a trick you use many times in statistical mechanics. Okay, minus I alpha. Okay, so it's the same transformation as before, but now we have a parameter alpha here, okay, which is a subindex here. So if we can take a particular limit, f of 0, okay, of an operator, okay, we just set 0 in these guys, and we just obtain f of 0 is just the operator, without any transformation. Okay? As we said before, f of alpha, dagger of the operator is going to be, okay, like we proved before, this one we just proved, it's just going to be the dagger in the inside of the transformation, okay? That's another property of this function here. And then we have some linear properties of this function, which are if we just superpose two operators, okay? This will be just the sum of those two. Okay? And the product, okay? Maybe this could be, we could make the proof of this guy is very easy, right? The proof of this guy, maybe just introduce a trick, okay? So remember that this will be e to the alpha s o 2, okay? E to the minus alpha s, okay? And then you can introduce a unit operator here. So we just call this O1. We introduce minus alpha s I alpha s. So the product is 1. Okay, and then we just identify this will be just the product of O, okay, times alpha 2. Okay, just mark this a little more neatly. Not 0 but alpha. Okay. Okay, so we're going to use now this function and the derivative of that function, f of alpha prime, which is going to be the derivative, to determine the function f. So you see, essentially we're going to invert this relationship here. This we're going to invert p as a function of c as a function of p's in order to find the solution for any function. Remember that this is a generic function, so this could be c or it could be a, okay? So we're going to find the solution, explicit solution for f, okay? And with the dependent of f, we would have solved the full problem, okay? So we will continue with the details next class, okay? Any questions here? Michaela had a question. When is the next homework due? Okay, I think, I mean, you check out please check out the homework. I think we have covered most of the details of homework number 3, okay? We can have a session on Monday to solve any remaining problems, but I think in principle we can shoot to turning it in by the end of next week. Okay, maybe it's too soon, but let's shoot for this one because I'm soon going to post the homework for this section. Okay. Okay. Any questions? I see we have a new student, Tevi. Is it a new student or is it? I hadn't noticed Tevi before.
It is my account, Mr. Esteban.
Okay, okay. So you're okay. Just I hadn't noticed your name before. Your screen name before. Okay, so see you tomorrow then, to continue this class. Okay. Bye bye.